Okay, welcome everyone. This is the AI and ML conference, mini conference that we're going to host. And this is a 3-day conference here at the Carey School of Business. We have our first guest speaker, Sridhar Sudarsan, who is the CTO of Spark Cognition. Sridhar is a senior tech executive and thought leader focused on defining and realizing strategies around disruptive technologies, including artificial intelligence, Internet of Things, and cloud computing. He has deep expertise in ML, data, and cloud platforms with demonstrated success directing game-changing tech initiatives. We'd like to thank Sridhar for sort of filling in for the spot last minute, for his generosity and for his time. If you have any questions, please feel free to type that in chat. We have this series is in collaboration with Professor Graham Warren and Professor Minghong Su, who are also on the call. And we also have other sections of BDML joining us today too. So without much further ado, please welcome please join me in welcoming Sridhar. Sridhar, please take it away.
Fantastic. Well, thank you very much, Advay. I really appreciate it. And again, just to make sure and confirm that you can hear me okay in the room.
Yes, we can hear you.
Perfect. All right. Fantastic. So thank you for that kind introduction, and good to meet you all. Hopefully you're all doing okay and having a great evening. So what I wanted to talk about today was go over kind of what is navigating the AI journey in an enterprise look like. You're all, my understanding is that you're all working on a variety of different sort of approaches and techniques on machine learning. And I wanted to give you sort of a perspective on a real world perspective and what that would look like. So there's a lot to unpack if you think about what does it mean to apply AI in an enterprise. And enterprise is kind of my expertise area, which is where I've spent a bulk of my 26 plus years in the industry. And over 15 of those by doing exactly what I'm just saying is around applying artificial intelligence approaches. It's a hard thing to do. So by saying that, I want to differentiate that I'm not necessarily referencing B2C type applications where it's really direct to consumer type approaches, right? So that's kind of the one area that I will focus on, and I'll cover a variety of different topics. This is a fascinating area, and just get you a little bit of an introduction into the kinds of challenges, the kinds of approaches, and the kinds of outcomes that I've experienced over the years in bringing AI at scale in an enterprise organization. So what does that really entail? Now, I thought that there's a lot of different sort of aspects. There's many industries. There's many different sort of enterprise areas that you can work on. So what I'll do today is I will, to just have a common theme, I'll take probably one example and I'll try and run it through sort of throughout the presentation, and then I'll zoom out and I'll show you kind of how it has applied or could apply in a bunch of other areas, right? So manufacturing is one that I picked. Could have been anything, but I just picked that. So first thing, and this is a couple years old, but it's still sort of relevant, is that at the senior leadership level, there's a very significant concern in manufacturing companies. And this is true, by the way, at energy companies. This is true in chemical. This is true in CPG. This is true in retail, across the board, right? The percentages are slightly different, but they're all pretty high, where they don't really have good visibility into the business. And that causes a lot of uncertainty and risk, right? Not to mention supply chain challenges, inventory issues, production issues, distribution issues, demand issues, and so on. So that's the way that, that's kind of me using this nugget as a way to introduce kind of one problem, and then I'll use that as a theme, and I'll make certain points as we go along. So if I think of a platform, and what does the AI sort of layers, what kinds of layers do you need to bring something to life, right? The center of all of that is your data. So in this case, you see that and if you look at any enterprise, they have all kinds of data sets. They have data coming from machines, data coming from manuals, data coming from tickets, data coming from images, from videos, acoustic data. You could have procedural data, you could have, forecasting, pricing. So think about all of these different forms of data, and immediately what it starts looking like is this sort of aggregation of structured, unstructured, time series, natural language, image, video, and so on, a variety of these data types. Now, there are different ways you can approach it, right? So I'm just going to take a holistic view here. And different ways you can approach it means every problem has a very specific type-specific data, and you can have a specific set of approaches that you can apply. So for example, if you're using structured data sets, you could apply regression techniques, you could apply forecasting techniques to those, and a variety of those. But if you have time series data, those might work, may not work, right? And sometimes you might have to even apply unsupervised approaches, and what does that look like? So that kind of becomes your core layer of um, a continuously evolving set of research approaches that you need to apply on these data sets that then generate certain sets of outcomes. These outcomes are now consumed by your business users. So again, for this purpose, if I take a manufacturing example, I think most of you are probably familiar with a production facility, at least at the outset, right? You don't need to know about the details of what is going on, but a production facility produces things. If it's an automotive production facility, it produces automobiles or assembles automobiles. If it's a CPG bottling beverage company like a Pepsi or a Coca-Cola or a Heineken or one of these, they're basically creating beverages, right? Or they're producing bottled beverages at the other end of it. If you're an aircraft manufacturer, you're producing aircraft. If you're a supplier, if you're a producer of valves and nuts and bolts or electronics, then you're producing that, right? So when I talk about a manufacturing production facility, that's really what I mean. It has many lines, it has many sort of SKUs that are, or SKUs or parts that they're producing or assembling at the end of it, right? So that's kind of just to level set for all of us. That's the theme that we would use as we go through this discussion. So what is central to all of these different systems? The central fact that we care about in all of these systems is the data. That's the most common thread that binds, these various sort of processes. If you go back, 100 years, 200 years, or even 300 years, around the beginnings of the Industrial Revolution, that data was all in people's heads. If you fast forward to today, that data is in a variety of different systems, proprietary systems, common systems, public systems, internal systems, external systems. It's still in people's heads. There are processes that are in place. They're in documents, they're in file systems, etc. The key point there is it's in a variety of different systems that is not necessarily always easy to access. But again, if I take sort of this, in this example of food and beverage manufacturing data, it's powered by that. So the work that you would do as a data scientist starts from some data set like that. You probably all have experience in looking at, let's say, Kaggle data sets or open source data sets, which are representative of some of these types of problems and challenges. However, what you're really seeing is a set of very highly curated and processed data sets. The real world is not always the same, right? Is not always that way. So what are some of the things you need to be responsible, you need to be thinking about and questioning and challenging, or that you will encounter that you will need to solve for, right? What does that look like? So to me, it's really about four things. It's the availability of the data, whether or not it's available. It's how do you use that data? How do you use the outcomes from that data? So this place is where you now start actually building your models. And four, how do you actually scale it and make it work not just in one project or one exercise or one demo, or one plant or one facility, but how do you make it sort of work over and over again, right? And so that's really the very simple way of looking at kind of a four-step process. So if I think about kind of now the, what does sort of availability of data really mean? And you've probably gone through this as an example when you process data in your data sets is, do you have the data, first of all? Now I'll give you one example. When we were working with a set of with a very large manufacturing company, consumer manufacturing company, CPG manufacturing company in the US, one of the first things that they came to us with was, we have a lot of data. We need to apply data science. Our plant is not running efficiently. Can you help us? Great example of a problem, right? Plant is running at 67%, which means there's a lot of room to improve. How do I get it to the mid 80s or early 90s percentage efficiency, which means can I produce fast enough because my salespeople are telling me that I can sell a lot more product if I produce it well. But we're having a lot of problems, so can you look at all of our data and tell us that? Great problem to start with, right? So the key thing is, do they have the data? Now they claim they do. Is the data sufficient? Well, here's where you start sufficient and is the quality of that good? And is it reliable enough for you to be able to produce your data science, to apply your data science techniques and generate sort of results that are valuable? And is it also not just a one-time thing, but is it something that will continue to work where you have that entire setup for the data is continuing to get generated, it's good quality, you're applying your data science approaches, and you're generating good results. So in this particular example, as I mentioned, they started out by saying, hey, we have a lot of data, very good, please help us. And we have a real problem. So it's a good place to be in, right? Because in the industry, unless you're working at an academic lab, there is business results that you're really, required to deliver. So we analyzed that data, and I'll tell you, one of the first things we recognized within a week or so was that, so this was time series data, just to unplug it a little bit more. It was time series data. Time series data means it's a set of assumed set of data that is coming with timestamps on it, and the timestamps have meaning, right? So for example, if a machine is generating data, then at every point it generates the data set, you can almost create the state of that machine at that instance in time. And what you're really trying to predict is when is that machine going to not work as well, right? So as an example. Or you could have another time series data sets that is sort of describing a behavior of a certain system or a process, and you're trying to figure out, when is it sort of deviating from a normal or an unexpected sort of behavior. So, and if you probably all have done sort of some machine learning work, you know what a feature is or a tag is, right? So in this case, these machines were instrumented, this plant was instrumented with 3,800 tags. Each tag, assume being for simplicity, data a sensor in that machine or in that, on that line, which had multiple machines. And 3,800 tags as a data scientist, you get very excited. This is great. I can do a lot of things with it, and it's continuous, and I'm getting, data within small intervals, and so I can do a lot with it. But I'll tell you, after a week, talk about how much of that is actually useful and good quality. Guess what we found is that the number of tags that were actually valuable out of 3,800 was 8. Not 100, 8. So what does that mean? It means that the rest of the tags, yes, there was data, but it's not data that you as a data scientist can actually use to generate meaningful insights. So from that purpose, it's practically useless. So what you really care about is what data can you use to actually apply the approaches or techniques in machine learning to generate the insights that are required for the problem that was originally provided. In this case, remember, it was all about how do I increase the efficiency, which means how do I reduce the amount of time that the operations are running, or increase the amount of time that the operations are running and reduce the amount of downtime that I have. So that's really the way that we were looking at it. But it gives you a good example of where the reality can be and the kinds of sort of data sets that we are dealing with in the real world. And it's not it's not atypical to find those kinds of data sets in reality and in the real world. So what does a complete sort of data set readiness system look like? And this is a methodology that I tend to follow, and I think, it's something that you will probably either explicitly or implicitly follow every time you encounter a variety of these types of sort of systems. So, you can start pretty much anywhere, right? You can pick the sensors. In this case, the sensor is what is generating a tag or a feature. It could be any kind of data. It doesn't have to be coming from machines. It could even be coming from your software generating logs. It could be coming from financial transactions, could be from anywhere. That generates data. You determine how the availability is, what the quality of that is, veracity of that. Can I trust that data? Is that data really generating the right set of results? One example of that, you often find that these sensors are very, very, very cheap, right? They cost almost nothing. So people throw sensors everywhere, but the sensors will fail, and it will generate sort of anomalous data sets, and it might show that there's actually a problem in the system while it never was to begin with. It was really the data generation piece that was incorrect, right? So veracity of the data is also very important. And then, of course, you have the infrastructure needs on how do you actually deploy it and where do you actually generate the visibility of this, and how are you actually providing the actions to the right users. So that's the whole life cycle. The spider chart really shows, in some cases, where you start from and where you want to get to. So the inside, the purple lines is one example of where, when we looked at one of the customers' data sets, we plotted on where are they on the readiness for each of these, and where do you actually want to get to is kind of the green. Right now, you don't necessarily, they're not always equal, but you want to get them to that point, because otherwise you're not going to get the right results. So now the next point is, how are you actually leveraging this data? So great, let's say we crossed that hurdle, we found the data, we got good data. We now figured out that this is a good starting point for us to start building models, to start applying, a variety of machine learning techniques, deep learning techniques, natural language techniques, generative techniques, could be any of those techniques. But let's say that you got there. What does that really mean? And how do you actually operationalize what you're generating? So this is kind of, what our second sort of set of challenges are. And I'll show you actually one example. I pulled this off of something we did in our lab. So back to this, this manufacturer that we were working with, a very interesting sort of problem. As I said, they had a bunch of machines. They had, they were producing, manufacturing sort of bottles of beverages, right? So if any of you have had um, bottled or canned beverages, each one of them is a different sort of SKU. So if you imagine, these machines are very, very, very long. I mean, they can run several hundred feet with many stations in between them, where you produce the liquid, you create the bottle. Sometimes they blow the glass in there, they shape it, they pour the liquid into the glass. There's a bunch of cleaning processes that happen of the bottle, of the lids, and all of those things. Then, there's sort of putting the lid on those bottles, and then at the end of it, there's a bunch of tests and so on and so forth, labels and so on, right? So that's kind of a typical way of how any of these lines would work. And one of the challenges was, we are having problems where we have, when these machines go down, we are trying to figure out what is causing it. So here's an example of what we recreated in our lab, right? We took a sprocket. Everybody probably familiar with what the sprockets look like. They're kind of like these spokes, and they sort of sit around the chains, and that's what makes these lines move, right? Now, a good sprocket looks like that, very nicely defined spokes. A moderate sprocket, after it runs continuously for a while, you start seeing this wear off. Looks like a bicycle chain type, sprocket as well. And then when it wears off a lot, it starts looking like that, and these chains start slipping, and it is one example of a cause of downtime, right? Now, it works differently on load. So if these lines have a lot of load, it will fail faster. If it's moving at a higher speed, it'll fail faster. These are very commonsensical sort of ideas, right? And so we said, okay, well, this is all great. If you apply now a supervised learning approach to a problem like that, what would you do? You would say, well, give me all the types of examples when this has failed. Tell me exactly when it's failed. I need enough of these so I can create a supervised model, and then I'll tell you exactly when it'll fail. Well, in the real world, in the industrial sector, unfortunately, there's not enough examples of failure that you can always review. I mean, take an example if you're working on an aircraft part um, failure prediction. You cannot go to the aircraft operator and say, give me all the times that the aircraft has failed, because it's likely either never happened or happened very, very rarely, like a handful of times. How are you going to build a model with something like that, right? You cannot build a supervised model. So in those examples, what you end up doing, which is kind of what we faced here, is you create one technique, right? This is one example, and I'm not going to go into a whole lot of detail on this, but it's one example of what we developed called a normal behavior modeling. So it's an unsupervised approach where instead of sort of learning from the mistakes and the failures or the anomalies, we actually learn what is normal. And then we sort of create and normal is really a representation of all of those tags and features that you have. And then you determine how you start sort of looking at constantly predicting what the normal would be, and then you measure what the actuals are. And now you find the residuals between the two, and that starts giving you a risk score at that instance in time. Now, this is happening, remember, sometimes every second, sometimes every few seconds, sometimes every few minutes. It depends on kind of how the machines and systems are running and what states they're operating in. But what you're now doing, what we are doing, is we're calculating the specific risk of that machine based on how much of a deviation we're finding from what we predict to be the actual normal. And that's what we're continuing to drive. And with any kind of enterprises, you cannot give them a black box solution. So you have to also give them a explanation. And in this case, the explanation is the feature importance of what is causing that, right? Otherwise, nobody trusts your system. So that's basically just a quick overview of what normal behavior modeling is. And this is a technique that, as an example, when we applied, we showed how you can see here, right? So this is now run in a real environment. We took this brand new sprocket. You start seeing the risks plotted over here as in the, can you guys see my cursor when I'm showing it, or not really?
Yes, we can.
Okay, perfect. So if you see in the training, it is all sort of still within a manageable range. When we then took out this sprocket, we replaced it with this moderately worn sprocket, you start seeing the beginnings of these risk scores that are being shown above this red line, which start showing that, look, there is the beginnings of a problem that we're detecting. And this is one of the things that is hard for a physics-based model to generate, right? A rules-based, first principles-based systems. It's hard for it to find, because a typical system works with a simple threshold. You give me a threshold on temperature, a threshold on pressure, a threshold on, a variety of different sort of parameters you might have. And that's really all it's doing, is it's either that or not, or it's a combination of those. This is now creating a model of that system at that moment and generating it. So it works really, really well to find these slow-moving sort of risk, slowly growing risk, which is very, very common in these kinds of systems. Now, and then of course, when you replace this with the most worn sprocket that I showed you earlier, you can see how it's sort of showing a high degree of risk. Now, this is very interesting because what now you need to determine is how usable is that insight that you're generating. So great, as a data scientist, what you've done so far is you've built a very good model that you think will apply in a real environment, that you can model and determine what the normal of that system is and generate when it starts, generate some kind of an alert, let's say, because you understand when the alerts, when it's reaching above the threshold and generating certain risk scores for you. So fantastic. As a data scientist, we all feel very happy that we're able to build a very cool model that would apply for this data set for this problem. Now, the next question, it doesn't stop there, is, okay, how usable are these insights? What do I do, right? Remember, we started with a very good problem. We overcame our data problem. We overcame our machine learning problem. In this case, it was we didn't have enough examples of downtime and exactly when that happened. So we took an unsupervised approach. Now we're saying, okay, what do we do with this? So now you have to remember anything you produce as a result of data science is only as good as when you put it in the hands of the real users that will actually either benefit or not benefit from it, right? Or benefit somewhat from it. So that's what this section is all about, is how are we making sure that these insights are actually usable? You've got to make it available to someone, whoever that someone is. It could be a salesperson, it could be a technician, it could be a marketing person, it could be a HR person, it could be a factory worker, it could be an operations person, whoever it is, right? Depending on the application. You have different types of interaction models. Like in this case, it was an alert. So an alert could come as a notification, could come as an in-app notification, could come as an email, it could come as a text. There's many ways of sort of translating what you just created into something that is usable. You might need to create an interaction with another downstream system that you might have, right? And sort of create a new work order. Okay, you created the problem, now create a work order in the system so that somebody can go fix that problem. That's an example of an integration. So this is kind of what it's all about in terms of how do you make it actually usable. So in this case, what we did was we said, okay, well, it's great that we figured out how to do this with these sprockets. But now what we do is we have to determine with the user is how early do you want to know about these problems? Because you could start sort of the threshold level for the risk. This is not threshold for each value. This is the threshold level for the output values. And what we're saying is you could set it anywhere over here. Anywhere in this spectrum is a good place to set it. The trick is also when you work with users, and we are all consumers of a variety of different products, so we know that is you have to trust the system. Otherwise, you're never going to use the system again, right? And I think we all do that. If we love something, we keep using it forever and ever until something next interesting comes along. But if we don't love it, we have so many other things to go look at that there's no reason for us to work with this tool or system or product or app or whatever. So that's where it becomes very interesting to look at the problem type. Now, in this case, it's a machine. You can set the risk at the right level. You don't want to have too many false positives because then that becomes, a great way for your users to stop using your systems. You also don't want to have too many false negatives because then you're not generating as much value to the users and the buyers of your system as you would expect. So this is an interesting, problem, which really depends on the types of context of the problem area where you're deploying something like this in. So in a manufacturing facility, there might be some degree of, early warning that you may need to determine. If you're in a safety, security, critical systems type thing, then they probably want the warnings a lot sooner than maybe another system that might be okay with waiting a little bit longer, right? So that's what I mean by the context of the results where your data science results are being applied and shown in a real world application will also make some decisions and determinations of when you're generating your alerts, when you're generating your actions for the people to actually start using it, right? So in this case, we work with the users to say, okay, well, this is kind of the place where we want the model to start alerting, because otherwise your model is just generating a bunch of outputs. Question is, what do you do with that, right? How do you make it actionable? So this is where, in this case, we created this band to start showing them where the problems start occurring. And then at this point, we make it even more extreme as a result, saying, look, we're confirming this as a risk. We're confirming this as a risk. You need to go work on it now. I'll give you another example. About 7, 8 years ago now, we did this. We applied this. We were very early in this stage, and there was a brand new turbine. If you guys are familiar with what a turbine is, it's this massive sort of machine that is used in generating power, right? So it was being used at a utilities company in the East Coast. And they had already, 10,000 plus physics models that they had deployed on that system. They already had another one company that was deploying a predictive sort of system that uses the same sensors. We went in and applied this sort of approach and technique using normal behavior modeling because we had never seen anything from that machine. That was a brand new turbine that actually came from the manufacturer and was deployed there. So we had no idea about it. We just created a model and we said, okay, well, let's deploy it and let's start running it and let's see what we get. We actually found a problem in about 4 months, and it was kind of in this, level. And we went back to them. They were like, oh, no, we've looked at all of our physics models. We looked at all of our other models, and we don't see any results. It's okay. We're all good. So we kept seeing it get to sort of this level, and it consistently kept sort of propagating. And now we went back to them again, and we said, look, after all, double, triple, quadruple checking, this is what we're finding. Now, the reason they were not willing to do anything is because it's not cheap for them to stop producing, investigate the problem, and so on. So second time, again, they pushed back. Third time, when we went back, all within, by the way, 10 days, they basically said, fine, we'll go look at it. And they actually found that there was, so these turbines basically rotate. They have blades, right, one after the other. And that blade is kind of, when it rotates, that's part of what is sort of generating power at the other end. But one of those blades was sort of coming loose from the rivet, and that was one of the things that was generating this alert. None of the other systems caught it. We did, and that if they had run for a little while, the next stage of it would be that blade comes off. And when you imagine a blade sort of flying in terms of a lot of metal rotating, it could cause fire, right? And so it's a multi-$100 million type of problem, and that's the thing that we helped sort of mitigate at that point. So it shows. Yes, sir.
Could I interrupt you for a second here?
Please.
We had a question from Young about the real-time data. I'm assuming that what you're doing here is you're collecting the data on the fly, right?
Correct. We are. In this particular case, yes, it was time series data that is coming directly from the machines, and these models are running automatically on the back. Correct.
And then what kind of frequency would you be reporting to, the engineers or the line staff who are managing the system? What sort of frequency of reporting are you doing there?
So the reporting is basically generating alerts. And what we do is we generate the alerts when we see the alert, the moment they see it, right? So what they get is the collection of the data can be at varying degrees of frequency. We've had these at 6 data points per second to sometimes we've had a data point per 10 minutes, right? It depends on the different machines. They're all over the place in terms of how they sort of generate the data and how much we need, right? What granularity of that data that we need. But when we then report out, there's a whole set of reports and monitoring and everything else that is provided for them at any time that they can log in and see kind of how the system is behaving. So at any time you log in, you will see exactly where that, so if your timestamp is here, you would see the point up to here. But the actual alert that gets generated, like this one, will go kind of based on what they've configured, and it could go into, as I mentioned, their apps, their notifications. They could see it in the system as well, and so on. So that's how the alerting works.
And then the reason, you discovered in this turbine example that it was a blade that had, the fir tree root of something probably had come to something. But you mentioned in one of your slides variable importance information.
Correct.
Are you using that to develop your reason codes?
Correct.
Do you ever use causal analysis?
We do. So in this particular case, so this is actually a great follow to that the slide that I was right after the one that I was describing earlier. But this is basically what we do as the reasoning. It's not in this particular case, it's correlation more than the causation. A slight difference there, because we're doing this in immediate real time. So when we highlight that there is a particular risk score at this level, what you see here, and these are some examples, the first sort of, let's say, half a dozen or so of these sensors. So as you can see here, these are magnetometers, 2 minutes, 5 minutes. As I mentioned, these are different frequency levels at which sampling levels at which we're getting the data sets. But the dark color indicates that that is the feature that is causing this risk score to be high at this particular time. So if I need to go investigate something, I would go look at the darker features that at that point of what I'm interested in. And those are the ones that are really causing my data science models to show that this is higher than that risk threshold versus the normal that I was modeling at. So that is the explainability, that is correlation. Now, at that point, you leave it to the technician to then apply kind of and validate or invalidate. And this is where your feedback loop learning comes in, because we have a thing called dispositioning the alerts. So when we alert, they can either accept it, they can say, no, it's not a valid alert. It's a normal, it's a condition that is abnormal from before, but it's not a condition I'm worried about, right? So they can label it like that. And when they do that, we take all of that in periodically and we retrain the entire model. And then now, those things sort of start impacting kind of what we show going forward, right? So these are the kinds of both explicit and implicit ways we look at explainability, because as I mentioned, if you just tell them that, hey, something is going on here, you're basically sending a lot of people on a wild goose chase, and nobody wants to do that, right? People want to know exactly what we need to do. Nobody has a lot of time. So you've got to point people to some place where you believe is the most plausible place where they can find an issue. Now, we actually have taken this further, and I'm only showing you a time series example, but we combine this with the prescribed part, where we actually now look at their NLP data and their natural language processing data, which comes from their not old, but their historical maintenance records. We look at their historical sort of manuals and incident reports, and we compare this pattern and this behavior to what fixes they have done based on the problems that, let's say, a probe accelerometer can cause, and how have they actually fixed that in the past. And we now actually provide the technician saying, not only is this the cause, but here's the ways that you have fixed it in the past. You all have fixed it in the past. And so this is a prescriptive way for you to think about, right? So that's, now you're getting into the causes, most probable causes, and how you actually sort of associate that and fix it. So there's an entire spectrum. I'm just describing the predictive part of it, but that's the prescriptive part of what we bring to the table as well. A whole different technique of what you apply in NLP. We use transformers now, but it's not time series data. It is sort of a different sort of algorithms that we have, NLP algorithms that we apply, right? And so that's kind of how you close the whole loop.
Cool, thanks.
Absolutely. So again, just to level set and back to the original sort of concept, all that I was describing right now uses machine learning and data science in the more traditional ways, right? Before you applied machine learning, I mentioned it was all about using physics-based approaches, which is really you take every one of those tags and you plot them separately, or you plot a combination of these tags, which you all know as having done some math that more than 4 or 5 tags, the number of combinations starts becoming untenable. So it's a very difficult thing, and that's why most people don't do all of them. They just do some of them and hope that that is the 70-30 that they can get. So as an example, in that same thread that I was showing you, the same set of examples that I was showing you, at all times, the temperature plots from the sprocket and the chain failure analysis never went out of whack. So if they were not using machine learning and not using data science, they would think that, well, all the fields are fine, no problem. But clearly you can see that there, and it's a fairly large spread in their normal sort of ranges, but you can see that they would not have been able to catch these issues until it was too late, right? So this is really showing you a comparison of that same time window that we found the problems, and when in a typical approach, you cannot find the problems, and why, what the work that you would have done with your data science actually is impactful, actually is valuable beyond what, most companies are actually doing, right? Many of them claim that they are using it, but they're not quite using it as well. And so that becomes my next sort of point, which is, how do you scale something? So that was a happy ending, right? We found a problem, you applied a data science, you went over your data problems, you created a nice sort of machine learning approach that worked for that problem. You figured out how the users can get the insights. That's all great. How do you now scale this? If a company has 100 plants around the world, if a company has, 50,000 retail locations, if a company has, 14 warehouses, how do you sort of apply this at scale? What does that look like? One of the points I just mentioned is the big difference between applying a machine learning-based approach versus a regular analytics-based approach is the learnability that you will have in your system. by definition, the biggest advantages you get with using any AI techniques is the fact that it's not just a rules-based system that will always provide the same output, but it is learning. And I gave you just one example, as I was answering the question on how we actually impact that. But there's many other ways that we can do it. That is just one example of it. How do you go beyond, one line in a plant? How do you go to multiple plants? How do you go to multiple regions? How do you go to multiple geographies? And, in the real world, there is no such thing as two things are exactly the same, right? Even if you have one company and they have 10 plants built very similarly, but they're not the same. I'll tell you another example. We had worked with a pump manufacturer about 5 years ago, and they are one of the largest pump manufacturers in the world. And they had done a lot of these tests at a new version of a pump or a new model of a pump that they'd created. And they ran through our models on that pump and made sure that the anomalies would all work and the thresholding and the alerting was all great. This was a facility in Dallas. They shipped the first batch of those pumps to a customer that they had in, I think it was in Germany. And, within the first 3 days, the customer reported a problem to them, and they came back to us and said, hey, we're having trouble because we weren't able to sort of detect what is going on. And what we realized was that some of the conditions that they had informed us about, so these are your tags, right, was very, very different from what that German customer was working in. So one of the fundamental differences that we found was the surface on which, they were actually running a lot of the tests to set the threshold level. The model still worked. It was just the thresholds that were different. The test that they were running was actually on carpeted floors. And these are pumps, right? So when you run these pumps, they're generating vibrations. It's all about sort of what that means to the temperature. It means to the output and the power that it's producing and so on. Versus when in Germany, it was deployed on concrete floors. And that caused a difference in terms of how the vibrations sort of impact and what that thresholds need to be. We were all sort of, stunned by why is it so different, because the models work really beautifully. The alerts were not generated right? So it's thinking about these bottlenecks and staying ahead of them and figuring out how you can apply them. Taking learnings to new areas. If you solved a problem for forecasting how a machine failure occurs, can you forecast or predict the problems on process failures? Very different from machine failures. Can you predict, one of the other things we do is predict prices, day ahead prices on renewables energy production. Can you take that and apply it to trading functions and determine if you can predict sort of the pricing forward there using AI? So it's really about solving one very specific problem and then expanding it and seeing if that same approach can be used to solve a different data set with the same characteristics, but in a completely different domain. And what are the nuances? What are the similarities? What are the differences? And how do you actually go about that, right? So, just as an example, if you look at a digital journey at a large manufacturing facility, this is how we work with them, right? We said, look, there's a whole methodology. You want to assess, you want to develop, you want to deploy, you want to run and learn. And then you keep doing that over and over again. And you do that in a staggered way, right? You don't have to always start with one and then finish one and then go to the next one and then finish the next one and then go to the third one. With AI, that is one approach you never want to do, which is do one at a time. Because when you do that, you artificially restrict the data, which means you artificially restrict your problem, which means you overfit your solution in more cases than not, which means by the time you get to the next one, the same answer, the same models and approaches will not necessarily work. More often than not, they don't work. I'll give you another example. We were working with a logistics supplier who were helping supply products produced in China to the mainland US. And their data scientist teams built this was their in-house data scientist team, built a fantastic forecasting model on ports and custom prices and so on for a batch of shipments. And they they found an 86%, they got an 86% accuracy on shipping of electronics goods, which is the test data sets that they had used, training and test data sets they used. Very thrilled, very excited. Now they went in and tried to apply that same thing to a real customer. This time it was a retailer for clothes. Guess where their accuracy dropped to? 12%. It can be that drastic. It's not just a, little sort of change, but that was kind of what it was, right? So the point is that there are many ways of sort of figuring out how you can apply it. This is kind of just to rehash the virtuous cycle that I mentioned. You've got to keep doing this over and over again. This is what makes, in my mind, machines that learn from humans, that learn from machines, and then the bar just grows higher. This is how we make each other intelligent. This is showing how you go from a very siloed system to a more consolidated sort of system where, again, the common thread is your data highway. On top of the highway are your AI systems and your AI approaches that are really generating sort of the outcomes. So this is hopefully gives you a little bit of a view. I did want to spend maybe 1 or 2 more minutes and I'll wrap up. But what we do as Spark Cognition, maybe I'll introduce that for 2 minutes and then I'll pause. But we actually focus on these 3 industries, right? We focus on energy, aerospace and defense, and manufacturing and retail. Within that, we solve problems all the way for the entire product life cycle, from innovation to quality, and the supply chain part, which is all about inventory management, all using the industrial platform, right? And as I mentioned, all we do is predictions, prescriptions, and automations. I gave you a few examples on predict. I described one example on prescribed. But that kind of hopefully gives you a little bit of an idea. And just to make it real, when I talk about scale, I really mean scale, right? So this, you can read a lot of these examples, but I'll take one of them. The first one is actually with an oil and gas company, Shell. Actually, it's public information. We work with them on a exploration project. So this is where they go figure out where to drill oil. It's a year-long process. And we found a 30x, not 30%, improvement in being able to identify how to process seismic data. So seismic data is kind of the data that gets reflected from sonars that are shot at the underneath of the ocean, gets reflected by the geology of the surface and gets pulled up. So we analyze that. So this is what is called an inverse problem, which means what you have is the effect, and now you're finding the cause, which means you're now finding out what the geology of the earth looks like so that you can figure out where the oil is so you can go drill, right? So that's an example of an inverse problem. To another one, a couple of these where, we found problems 7 to 10 days in advance. So remember that Sprocket example? In these production facilities, we're finding those problems 10 days ahead of time, consistently, not 10 minutes, not 10 seconds, 10 days. And it's very real, right? It's very important to be able to do that, and so on and so forth. So again, without sort of going into every one of these are the kinds of scale and the real value that I mentioned at the beginning that really makes it very interesting, where the fundamentals of all that is the data science techniques that we applied, which is necessary but not sufficient. So just a bit about who we are and, just some of the types of customers that we work with, as you can see across a variety of these industries, some very large names. I'm sure you'll recognize some of them. But with that, I will stop sharing and just wanted to say thank you very much for the time. And I'll open it up for Q&A.
By the way, would you like to take care of the Q&A?
I'm really sorry about that. Is it better now?
Yes.
Okay.
Much better.
Thank you so much, Sridhar, for that really informative talk. I think one question that has popped up is, could you explain a little bit about how you would prevent sort of the catastrophic forgetting that you mentioned that resulted in a drop in the performance of these algorithms when they were being tested on a new plant?
Absolutely. So this is the logistics example that you're describing? You're
Yes.
referencing? Yeah.
Yeah.
So Look, that was something that I was not involved in exactly what they did, but I could recognize it very quickly from what they told me as to what they could have done, right? That was not something we did, but now we're working with them to kind of figure out how we fix that. But the way that the reason I think that happened and that drop, which is, as I said, very common, is because what you tend to do is when you have a data set for training your models on, and you're really focused on, again, the metrics of what you look at is also important. So if you're really focused on the metrics of accuracy, let's say, or precision or recall or some combination thereof, but if in this case it was accuracy, the thing that you end up doing is, because it is a training data set, you tend to get the best accurate results for that. And in doing so, oftentimes you overfit the model to it because you don't have enough variety of the representative sample of data sets. So for example, in that particular case, they overfit the model so much into this electronics parts provider. And I mean, I'm not going to even pretend to understand all the nuances, but you know, we all know based as just general sort of information on when you're shipping, containers with, or if a company is trying to manufacture and produce a part in electronics components in China and then ship that, let's say, to a customer or a set of customers in the US, it has a certain routing that it goes through. It has a certain set of customs it has to pay. It has, there's all kinds of geopolitical challenges causing, different routings that you need to happen. And so a lot of these analysis. Now, when the data science team probably got that, they were asked to come up with the best possible way, and they kind of knew the answer, right? Because it was training data, so it was already historic, and they knew kind of what it should be. So very likely they would spend multiple attempts to get it as close to that as possible, and they ended up overfitting the model. Now, when they applied it at a clothing retailer, perhaps some of those variable factors did not apply in the same way as it did for electronics shipments, right? Customs are very different countries and ports. I mean, these are very, very complex rules. So when you did that, it very likely sort of missed some things or over computed some things, and that's what caused the drop. So when that drop happened, clearly they just said, oh, well, the model is wrong. My assertion is likely that you wanted the right sort of representative sample sets. So you're getting at least closer to the answer, maybe not as high an accuracy on the first pass, but at least your breadth of coverage is probably more. Now, they might have got a higher accuracy if they'd focused on the next customer being an electronics component, but I don't have the details of if they did that or not. So this is me sort of providing my assessment based on what I've seen. But we've gone through this, over the years so many times now that, I mean, I've heard this from customers saying, oh, this worked amazingly in the lab, but then when we put it in our first store, we did not get the right models. It has worked with vision models, right? When you do object detection, classification, works great in certain conditions and environments. You put it in real life, you have sunlight, reflections, you have colors, variations, doesn't work very well. So how do you sort of work through that is by impacting and increasing your representative sample. And this is one of the areas where actually generative AI techniques have really helped, right? Because you can generate and create samples where they don't quite exist. I'll tell you, we do this sometimes. So one of the approaches we take is for visual models, so computer vision models. And one of the types of detections we do is for smoke and fire, right? You have video cameras that are all over the place. Can I detect smoke and fire even at a very small level and actually warn people ahead of time before it becomes too late? And we do that, right? We've successfully actually provided a lot of preventions. I would say at least 6 preventions that we've done over the last year, which is fantastic. We also still do get some false positives, especially in the indoor areas, because sometimes these fires look like a different color, there's reflection and all that. So now you cannot ask somebody to produce fires and train on that. So what we do is instead we use generative AI. So hopefully that gives a little bit, context into that.
No, absolutely. Thank you so much. I think, so in short, it's when you know that the model doesn't work, probably look into the data and see how you can do better data engineering to improve on your model performance.
Yeah, data engineering, expanding the data sample size, perhaps the approach, even the data science approach you might have taken may not necessarily be the right one. So you might have to try a few different things to get there, but there's a methodology to doing that. Absolutely, yes. That's
Awesome.
correct.
Thank you so much.
Yeah. Could I jump into the question here? I think that a lot of folks, in our programs are fearful of where AI and ML are going. The story that you seem to be telling us today, if I look at two types of humans in your workflows, you've got the customers, the users, and you've also got your data scientists. It seems to me that if you look at that virtuous cycle, that these are it takes time, it takes patience. The space, the roles that you're carving out for the user, let's say in the turbine example, you're sort of ultimately relying on the human for validation, verification of what the failure is going to look like. The human who is in the data science role is being asked to stick around, be creative, to be very context sensitive, to carve out those roles for the human. Is this a fair takeaway from what you've said?
Absolutely. I think we are still not quite at a point where there's a lot of autonomous decision making that exists. There are some. There's definitely are some, but in other cases, I think where the mindset of a lot of the decision makers are, they still would want to have a human making the final call, right? In many cases. So in those areas, what you want to do is equip that human with the best possible set of data or metrics or outcomes or insights that they can make the right decision on, right? I mean, this is true for any of our decision making, right? I mean, whether you're deciding to pick a college you want to go to, or pick a restaurant you want to go to, or which are very, the restaurant you want to go to, maybe not as sort of impactful other than when you like the food or not. College you want to go to, big impact. Where you want to work, what kind of safety precaution you want to take. One of the things that we have with our visual AI is we actually provide safety and gun detection, right? So if somebody's actually carrying a weapon and so on in a place where they're not authorized to carry a weapon, in those cases, you want to know those as soon as possible, right? Now, the extension of the autonomy of the decision making, well, if the system detects it, can I actually connect to the door IoT system and shut the door? Or open the door, depending on which side of the door you found the person with a weapon, sort of, and where the rest of the people are, to minimize the impact or neutralize the impact completely. So this is where I mean by there's always a downstream set of decisions, and how do you actually sort of determine that? But in terms of roles, and I think this is also if I can take this other question that comes from Young on what skill gaps do we observe? Because this is kind of, Graham, to one of the things you were asking here. I would say that it's a great question because there's a lot of skills that are required still in this day and age. So even in the narrative that I just provided to you, on the data side, there's multiple different areas of specialization that still is required, right? On the data administration side, the data science side, the data cleanup side, the data engineering side, the data scale side, the ability to, so that's all on the data and the data science. Beyond that, now you've generated models, the whole machine learning operation side. Okay, if you produce these models, how do you make sure that you're in an organization? Now we have systems where we have over 200-300 models running. And how do you make sure that these models are managed right? How do you make sure that you detect model drift? These are models, right? These are not rules. So in a rule, if you say that 1 + 1 is 2, it's always going to produce 2. In a model, it is a probabilistic response. So which means by definition, and if I go back to that normal behavior modeling example, you're going to sort of have to assess where the drift is in the model because the context and the conditions are so different from what I trained it on that I'm not going to get the right results. So you detect that, then you retrain, you figure out what's the right time to retrain, you figure out how you would retrain, and then deploy that so that it's a continuous learning system. So that's a whole set of skills around not necessarily building the best models, but managing the models across the board and figuring out how you can bring those to life, even within the users, right? We hear about jobs and things are getting automated and people are losing jobs and certain skills are going away because AI systems are taking in. If you notice the kinds of examples I referenced, it's actually putting these people at a higher decisioning authority, or even within a task that might be running a machine or operating a machine, right? So when I say decisioning authority, I'm not just talking about executive levels. I'm talking about very simple jobs and tasks. It's taking away from doing the mundane to doing more intelligence that we as humans possess that we haven't quite yet been able to model in these systems. So that skilling, whether you're in a medical or healthcare practice, a finance practice, a manufacturing practice, a retail practice, an aerospace practice, it doesn't matter. What I think is changing completely is how do you bring this data science thinking into the role that you're playing? And that is a big skill gap that we see today, right, in the enterprise, in the industry. And I think that is the kind of skill gap that as each of you are going out into the, after you complete your education and go into the real world and work in different areas or become entrepreneurs, bringing that thinking in to then question, why are we having the right data? Is the data available? Can I trust this data? How do I make sure that I have data at scale? How is it continuous? Am I applying the right techniques? Is this the right model? Am I producing the right results? Are these results valuable? Am I able to make these results sort of consistently valuable for the user? That mindset of framework that I just described to you is a set of thinking that I think you will need to bring into every skill, no matter what type of role or job or entrepreneurship that you're undertaking as you go forward. And I think that will just make every one of it, it needs to become more natural for every one of us to incorporate into our core sort of DNA, so to speak, if I can use that term. Hopefully that helps, Young, to answer the question you asked.
We have another question
Time
from
for one more question.
Yeah, I think we have another question from Professor Zhu. That's regarding the NLP for prescription. What NLP algorithms would you suggest for students to master?
I would say, there's a lot of transformer-based algorithms now that are obviously significantly faster than they ever were even a year ago. So I would sort of look at those and the transformer-based sort of techniques are evolving very, very rapidly. There's deconstruction. There's a lot of these that we were doing fundamentally now has become a lot easier to go do. But it's really, again, if you look at generative techniques on prescriptive approaches, prompt engineering is a big area that I would sort of look at and learn and understand. Looking at RAG-based approaches is another one to sort of consider in terms of how do you constrain the results that you get. Let's say even if you use some of the sort of available models that are trained and so on, it's really about how do you tailor it to what specific areas that you're going after, which is still a long ways away from seeing success, right? I think what the ChatGPT release has done over the last year has just caused a lot of it's a hype cycle, right? It certainly is a hype cycle where the good news is everybody's now aware of something like this. The bad news is people don't know exactly how to sort of bring it to use within their areas, right? And I'm talking about more enterprise areas now, not the more just sort of general common areas that, where we see where the risk is lower. So if you take these kinds of things, if somebody is repairing an aircraft part, when they ask a ChatGPT or a prescriptive guidance type of result, you don't have the tolerance for it to be for it to be a incorrect answer. The tolerance level is low. So how do you actually apply those guardrails? That's where, RAG-based approaches come in. But the bar is very high, right? If somebody is sort of doing a diagnostics problem in the medical healthcare space, you don't want it to be maybe it's right, maybe it's wrong. It's not like picking a restaurant as a prescriptive guidance, right? So it's a spectrum of sort of space. I would say that when I reference these examples, I'm talking about these enterprise areas where the criticality and the tolerance for incorrect answers is much lower. which requires and necessitates you to think very differently. So I would say those are some of the areas, at least, that might be that are very relevant today.
By the way, would you like to close out?
Sure. Yeah, I think should we wait for any more questions, or does anyone in the audience here have any other question? Okay. So Sridhar, thank you so much. That was a really informative, really appreciate you taking the time today to talk to us and share everything that's happening at Spark Cognition and sort of share your experience and guidance with all of us today. Oh, I think we have one question from Young again. Sorry about that. So the current AI market is very profitable, but do you think for companies developing AI, will they experience survival of the fittest in the future?
Absolutely. I mean, I think there's still a long ways to go. This is a $6.4 trillion market over the next 6 years in this decade alone. So there's still a lot of innovation left. There's a lot of growth left. There's a lot of realization of these AI in the real world, as I've been describing, some very, very simple examples, but this is just the beginning of where we are. So there's a lot of opportunity here. It is definitely the profitability will continue to sort of grow and follow the market cycles as it has with many other trends. But absolutely, I think there will be consolidation. There will be more sort of diversification in terms of the types of challenges that we realize, and I think that'll follow a cycle. We're at the early stages of this. So good luck to you all, and I hope you all have a fantastic career as you go out and work in the space of AI, and we'll look forward to sort of seeing all the fun things that you go do.
Thank you so much, Sridhar. This is really super informative. Thanks for your time. Really appreciate it.
Thank you very much, Graham, and thank you, Adbay. Bye.
Thanks, Sridhar.
Have a good night, everybody.
Good night. Yeah.